All right. We've seen this before. We've saw that MGH, which is the distance from the surface. But what if we wanted to? Maybe here's Earth, and maybe wanted to fire off a cannon or something, and fire some object into space, and we'll call this point P. This has some m and some mass, and this has some mass. And to calculate the energy, we'd be looking at the work done on the ball by the gravitational force as it travels, and we'll say from point P to an infinite distance out here at infinity. Since the gravitational force, if you remember, I'll go ahead and write it down. Since it's dependent on its position, it's going to change, right? That means we need to integrate it. So let's take a look at work. If you remember, our definition is equal to our force, which is a function of r, and dotted into dr, the displacement. And we'd be looking at from some distance r, so that'd be our lower limit, to infinity. If you remember, we can say that f dotted into dr is equal to f of r times dr, or we can just simplify the dot product as the cosine of the angle between them, or phi. In this case, phi is equal to 180 degrees. And what we end up with, excuse me, is f of r dotted into dr is equal to, we substitute our force of gravity in, we get a minus g because it's pointed downwards. I'll put it on a free body diagram there. Times the big mass times the little mass all over r squared. And then times dr. Now let's substitute this all back into our work equation. So we need to integrate it basically, where the work is equal to, we can pull out the constant -1, the constant g, we can pull out the masses because they're not changing, and integrate from r to infinity, just the 1 over r squared with respect to r. And what does that give us? It gives us a 1 over r function. And we can evaluate that from any r out to infinity. And we, at the upper limit, get 0, and at the lower limit, get g big M, little m over capital R. So really just the work to take an object from some position P out to infinity would be equal to g m n over r. Okay, that would also be equal to the potential at that point, right? So the work done to take something from that point, from point P out into infinity, would be the same as the potential, or the potential energy, right? So if we're dealing with very large objects, or it doesn't have to be large, if we're dealing with stuff that's not on the surface of Earth, how about that? We need to calculate the potential, or the work done, in this fashion right here. And if you remember, I gave you a definition a while back, where we can find what a force is if we know the potential function. Where we use the derivative with respect to the potential. Of our potential for this thing here. Minus G, big M, little m over R. And when you take the derivative, you get the force of gravity. If you ever forget one, you can figure it out from that's just it works for any force, right? Any conservative force. And what do I mean by conservative? Let's go with the metric. Conservative means a total path dependence. Path independence. That means, if you remember, doesn't matter, let's say this is Earth, it doesn't matter if we bring the object directly up from point 1 to point 2, or if we decide to take some path like this. The potential is the same. The work done is the same. So gravity is a conservative. Your book covers another interesting topic. If we wanted to make sure that we launched a projectile or a rocket with enough speed to leave Earth, right? How do you calculate that? Well, we would look at the potential. And then you say, once the projectile reaches infinity, we'll say that it comes to a stop. The velocity is equal to 0. So it has no more kinetic energy. It has no more potential energy because its infinite separation distance brings the 1 over r squared to 0, right? So what we can say is the kinetic energy plus the potential energy would be 1/2 mv squared, right? It's moving, it has mass, therefore it has kinetic energy. And for our potential, we need to put in the minus g m little m over r. And it's going to come to a stop, and it's going to have no more potential. So we can solve for the velocity. And you get the velocity, or what's called the escape speed, or escape velocity, as 2 times the gravitational constant over the big mass over your starting point. Notice this is little m independent. It doesn't matter what mass you're shooting off, and if you remember, mass canceled out a lot when we looked at energies. Right? Okay, the last thing I want to go over is Kepler's laws of planetary motion. There's 3 laws. Kepler was a brilliant physicist and astronomer, and worked on laws to govern the motion of the skies, or the bodies that are in the skies. You just use a telescope and took lots and lots and lots and lots of data. And later, this is before Newton, right? Let me double check. So Kepler, I'm just getting some history out for you. Kepler was 1571 to 1630. Newton was 1642 to 1727. And in between here, Tycho Brahe, I can't remember how to pronounce it. He took this information that Kepler had figured out and made these 3 laws later to bear Kepler's name, the Kepler's laws. So what do we got? Law number one says that if you have, and this just relates to two masses with a gravitational force between them, right? Planets, satellites, uh, things, objects in free fall around each other. The first law is called the law of orbits. And it just says that planets move in elliptical orbits. And they do this with the sun at one of the focuses, one of the foci. So what do I mean? If you remember, we have an ellipse. This could be the path of, it's a little exaggerated, but let's say this is the path of Earth. It is not circular, it is definitely elliptical. And when we create an ellipse, if this is the path, we need an object to go about. And so, if you remember, an ellipse has two foci, and we need to put one object at the center of one of those, and that would be our sun in this case. This works for the Earth-Moon system. This works for any two bodies. We can add up all these bodies too, and there's a law, the principle of superposition. It gets tricky when you get over more than two bodies, though. And if you study physics a little bit more, you'll study the two-body problem in depth. That's Kepler's first law. This is the shape of orbits when gravity is involved, and the fact that there's nothing at one of the foci, but at the other is our more massive object, of which the other is traveling around. Okay, the next one's got a little math to it. It's called the law of areas. And it says, I'm going to draw it out for you, but a line that connects a planet to the sun sweeps out equal areas in the plane of the planet's orbit in equal time intervals. So it sweeps out equal areas in equal time periods. And I'll draw it to help make sense of this one. But in other words, the rate dA dt, the area, the rate at which it sweeps out the area is constant. So if we have a ellipse, this is the path of, we'll just keep using Earth. And we'll put sun at one of the focus. If I look from, let's say, it starts here at 1 and it goes here 2. If I was to calculate this area, and let's say it took some time delta t to travel from 1 to 2, and then I look over at some other time, let's say from 3 to 4, but they have the same delta t, then the areas made inside these triangles are going to be equal. So we can add some math to this. Best way to think about it, in my opinion, is just that the planet sweeps out, as it moves, it sweeps out the same amount of area in the same time interval, delta t. In a longer time interval, they would each sweep out a little bit more, right? From this, we can say that Kepler's second law is indeed equivalent to the conservation of angular momentum. Conservation which we just learned about, right? But you should probably remember it sweeps out equal areas in equal times. Okay, the next one would be the law of periods. I'd go into these in a little bit more detail, but we're running out of time in the semester. If you take astronomy or any more mechanics courses, you should go over these in more depth. The law of periods says that the square of the period of any planet right, the period is how long it takes to go around one time. The square of the period is proportional to the cube of the semi-major axis of its orbit. And I'll draw this one out in a second too. All right, law of periods. The square of the period of a planet is proportional to the cube. And I think you probably did this in one of your first labs where you probably had to do a log-log plot to get a linear line, because what you were doing was looking at something like t squared is proportional to r cubed. We're missing a couple things in here. I'm about to get those for you. Saying or starting with force is equal to mass times acceleration. This is Newton's second law. And then we have our gravitational force. Is the only force acting on the body. That's going to equal the mass times the acceleration. But let's use the acceleration is omega squared r. We're talking about things rotating, so let's use omega. That's the angular velocity, right? We end up with we need one more substitution. Omega is going to equal that 2 pi over the period. So I'm going to put the acceleration here, omega squared r, and then we're going to substitute in omega for omega squared. And what we'll end up with is the period squared is equal to 4 pi squared over big G over big M, all times the semi-major axis cubed. So we have a proportionality of t squared is proportional to r cubed. This holds for, and all of this works for ellipses, and if it works for ellipses, then it works for circles, right? And a circle is an ellipse with no eccentricity at all. I just wanted to point out one more thing. And that is something in orbit has energy also, right? It's got kinetic energy equal to 1/2 mv squared. It's got some rotational energy also of 1/2 I omega squared. And it has potential, like we just talked about. Potential is equal to Gm minus Gm little m over r. Now, we do have if no external forces are acting on it, we do have a conservation of energy. And as Kepler's second law said, we have a conservation of angular momentum also. Pretty interesting stuff to take a look at chapter 13.8 and Einstein's views on gravitation. He basically, in very few words, I will put it. He says that gravity is the result of a curvature of space-time. So take that opportunity to read that. It's not going to help you solve any problems in here, but if you are studying physics, you're going to want to know about as much about this guy as you can. That pretty much sums up gravity for us. Oh, I guess there's a really cool example. So Einstein actually said, okay, we're going to have an eclipse someday. Here's Earth. And the moon is going to be blocking what we can see of the sun. Well, if that's the case, let me actually do this. If that's the case, and gravity is indeed a curvature of space-time, let's put a telescope down here. He said, on this day, when we have an eclipse, we should be able to see the stars behind the sun. And indeed we do. So even though we cannot see around the moon, right? Light doesn't just bend around it. The sun is actually great enough to bend those light rays. The force of gravity on it. So it kind of proved, it did prove that there is some, that photons, right, are affected by gravity themselves. And we call this gravitational lensing. You can actually look around, you can look behind stuff by using the fact that supermassive objects, got to be something like the sun or bigger, black holes, actually will bend the light and allow you to see behind. There's some great images out there if you were wanting to look at this more, but gravitational lensing exists. So the final question is, do we understand what's actually going on here? Should we attribute the gravitation to curvature of space-time due to the presence of mass or to the force between masses? Should we attribute to the actions of a fundamental particle called the graviton? The theories so far we've talked about have been very successful in describing everything from apples to star motion, but they don't work on the cosmological scale, and they don't work on the quantum scale, meaning very small. In that case, we have to resort to quantum mechanics and cosmological. We have dark matter. Right? I'm not going to get too big into that because I'm not a astrophysicist, but there's unaccounted mass out there in the universe. We can account for it, but we just can't detect it in a way other than the fact that we know that there's something causing a gravitational field or a curvature in space-time. All right, so that sums up chapter 13 and the gravitational force.